Hi, I'm Sophie and you're watching Science Today. Here's something to think about. Can you accelerate without changing your speed? Well, we're going to find out. So acceleration is defined as the rate of change of velocity, and velocity is a vector quantity, so this means it has both magnitude, so the speed, and direction. We can think about acceleration and velocity and position and how they're related using calculus. I know that might sound scary to some people, but if you've learned the basics, then it's pretty straightforward to go between the three of them. So, starting with displacement, we can differentiate this to give us a velocity. Then, once we have the velocity, we can differentiate this again to give us the acceleration. Acceleration is also the second derivative of displacement and is measured in meters per second squared, while velocity is measured in meters per second and displacement in meters. So we can also derive the equations of motion using calculus. First, we can start with our definition of acceleration, which is the derivative of velocity with respect to time. Then we can integrate both sides with respect to time. Since acceleration is a constant, we can take this out, and the left-hand side will have limits of time t and 0, and the right-hand side will have limits of the final and initial velocities. Following this through, we get v equals u plus at, which is our first equation of motion. For number 2, we start with the definition of velocity as the derivative of displacement with respect to time. We then set this equal to the first equation of motion, which is u plus at, and integrate both sides with respect to time. The left-hand side has limits of the displacement and 0, and the right-hand side has limits of the time and 0. So then, following this through, we get the second equation of motion, s equals ut plus a half at squared. For number 3, we start with our first equation of motion, and we square both sides. Then when you multiply out the brackets, you can see that it gives us the definition of displacement, which we found in the second equation of motion, s equals ut plus a half at squared. So subbing in for displacement, we get v squared equals u squared plus 2as, which is our third and final equation of motion. So let's go through a quick little exam question, just so we can get some practice using the equations of motion. As a set of traffic lights change to green, a car accelerates uniformly from rest along a straight road at a meters per second squared. At the same instant, a lorry travelling at a constant speed u meters per second overtakes the car. Find an expression in terms of u and a for the distance travelled by the car when it draws level with the lorry. Okay, so we know at time of 0 seconds, the distance travelled by both the car and the lorry is going to be 0. So we can say at time t, for the car, the distance it's travelled equals ut plus a half at squared, which is our second equation of motion. But since the question says that the car starts from rest, this tells us that the initial velocity, u, is 0. So this means that the distance the car travels at any time t equals half times acceleration times the time squared. We can do the same for the lorry. So the distance that the lorry travels will equal ut plus half at squared. And then if you look at the question again, it says that the lorry is travelling at a constant speed. So this means that the acceleration must be 0. It also says that the speed is u, so we can sub both of these in to give us the distance equals ut. Rearranging this, we can get time is equal to displacement over u. Then, to find the distance that the car and the lorry draw level, we take our equation for the distance that the car has travelled at any time t and sub in t equals s over u. So this gives us s equals half a s over u all squared. Then we can multiply out the brackets, and rearranging to make the distance the subject, we get an expression for the distance as s equals 2u squared over a. And that's it. So here's a recap of the equations of motion that you need to remember. First one, v equals u plus at. Number 2, s equals ut plus a half at squared. And number 3, v squared equals u squared plus 2as. For advanced higher physics, you need to make sure you remember these and also the derivations that were at the start of the video. So what about our question? Can you actually accelerate without changing your speed? We can rearrange the first equation of motion to give us acceleration equals v minus u over t. And we know that acceleration is the derivative of velocity with respect to time. So this tells us that acceleration must be the rate of change of velocity. We need to remember that velocity is a vector quantity, so it has both direction and magnitude, and speed is a scalar quantity, so it only has the magnitude or size. So in this case, the speed is constant, but the object is constantly changing direction, so that means the velocity must also be changing. And since the velocity is changing when an object is moving in a circle, this means that it must be accelerating. Circles! Who knew? And that brings us on to the next topic we're going to start, which is circular motion. So, hope you join me for that, and yeah, that's it. Hope you've enjoyed and see you next time.